The inductance per unit length is an important parameter when dealing with transmission lines. So let's look at calculating the inductance per unit length for a simple parallel wire transmission line. Parallel wire transmission lines were very common when I was growing up. A twin lead antenna wire is a type of parallel wire transmission line, and every house would have an antenna on the roof and one of these twin lead antenna wires leading to the TV, and that's how we would get our TV stations. We would get 3 stations, ABC, CBS, and NBC. Actually, there was a 4th station, a PBS station, but nobody watched that. Here is a look at a cross-section through the transmission line with one wire at x equals 0 and the other wire at x equals d. The current is coming out of the page at the wire at x equals 0 and returning into the page at x equals d. So we know that the magnetic field, due to the current flowing through the wire at x equals 0, will be counterclockwise circles around the wire. That's depicted here in this figure. And we've done it many times. You can just use Ampere's circuit law to get the magnetic field intensity as I over 2 pi x, and then multiply by the permeability, and let's just assume it's free space between the 2 wires. And there's a similar magnetic field intensity due to the wire at x equals d, but now the magnetic field lines will be making clockwise circles around this wire. We can get the total flux by finding the flux between the 2 wires. And if we find the flux just for one wire, all we have to do is double that result to get the contributions from both wires. So let's take this surface between the 2 wires and figure out how much magnetic flux is going through it. And the length in the z direction will be L. Our differential surface element will be dx times dz, and it will be in the a sub y direction. So the magnetic flux through this surface due to the wire at x equals 0 will be the integral of b dot ds over that surface. So let's substitute in for b and our d sub s, and we're going to integrate in the x direction from a to d minus a, that's the spacing between the wires, and from 0 to L in the z direction. So ay dot ay is 1. We'll factor out mu 0 I over 2 pi, that are constants. This integral will be the natural log of x. This integral will be z, which will give us just an L. So here is that flux through that surface S due to the wire at x equals 0. Now the wire at x equals d is contributing the same amount of flux through that surface S. So if we double this value, we'll get the total flux through that surface S. So here's the total flux through our surface S. The flux linkage is the same as the flux in this case, so the inductance of a segment of length L of our transmission line is this magnetic flux divided by I, or mu 0 L over pi, the natural log of d minus a over a. To get the inductance per unit length, we will take this inductance for a segment of length L of our transmission line and divide by that length L. So our inductance per unit length is mu 0 over pi, the natural log of d minus a over a.